Okay, welcome back. So I'll just do a few more things with higher order functions and then I'll give it a break. Higher order functions were mainly invented to torture students. No, that's not true at all. They're very useful. But there's only so much of a good thing you can have. So I'll do a couple more examples with higher order functions and then I'll move on to the second theme, introducing recursive data types. So here's a definition of a function using map. Shout, S, takes a string S, and applies the toUpper function, a character-to-character transformation, to every element in that string. Remember, a string is just a list of characters. So if I feed in this list of characters, I'll get out this list of characters. Okay? So that's what the shout function does, defined by map toUpper. Okay? Yeah, okay. Now, if we actually look at what the definition of shout, how it's defined using a two-argument function, map. And so we can picture a two-argument function as, well, take the first argument above with a short arrow. So that's the first argument, and that's the second argument. Okay? So I'm going to draw it as a box. And the purpose of these pictures is to give you an intuitive feel for this notion of partial application. Okay? So another way of defining shout, which is identical, it just looks a bit different, is to say that shout is equal to map toUpper. Okay? So map is a function with two arguments. But if I only give it the first argument, then the result of map toUpper is a function. So this is a function, and all I'm doing is giving that function a name. I'm calling it shout. Okay? So it's a bit similar to one of the examples we had earlier with function composition. We defined odd to be equal to something, something, something. Here I'm defining shout to be equal to something, 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 and that something, something is a function. Okay? So I noticed last week that people found that a little bit hard to grasp when you take a function and give it one argument but not both arguments. So the way that I'd like you to think about that is in this picture here. I've defined shout by applying map to one of its two arguments. So there's the argument that I've applied it to, and this is the argument that is missing. So when I apply this one argument input to map, what I get back is a function waiting for that second input, and it will give us a result. So this is the shout function. The second input will be fed into map, and the result of map will be the result of the whole function. Okay? So that's the way you should think of partial application. That's application of a function to some, but not all of its arguments, according to its definition. Any questions about that? Okay, and I've updated the slides. I haven't put them online yet, but I'll update the slides from last week to include these examples if you want to look at them on the slides. We went through many things similar to this in the Kahoot, so I won't do that now. All right, so let me just look at maybe one more example. So this is the file from last week, and I'm just going to continue a little bit from it where we talked about higher order functions. That might be useful. There was a string that I defined. I might come back to that. Okay, so we've talked about function composition, sections, and so on, partial application, hlint. Okay, so let me give you a little example of a function to illustrate something to do with precedence. So let's suppose I want a function that takes a string and gives me the first three lines of that string as a string. So a kind of summary of the string. Okay? So it takes a string as an argument. I'm going to convert that string into a list of strings, one for every line. So I'm going to use the function lines of that string. Let me just stop there for now. Does it compile? It does. 3 lines of song 2. Actually, all it does now is just break that song into its lines. And I'm going to take 3 of those lines, Let's try that again, reload that, run it again. I've got the first 3 lines, and now I'm going to join them back together again with unlines. Now this is something you've probably done a lot. You need to keep putting brackets in. Now what would happen if I left out the brackets? Well, it's an error. But why is it an error? Why did I need the brackets in the first place? Let me zoom in a little bit on that so we can see it better. Why did we need these brackets around this thing here? Well, the reason is that the function application operator, that invisible operator, associates to the left. So if I leave the brackets out, what it's doing is applying the function unlines to this first argument. Remember, functions can be arguments. We've just been talking about higher order functions. So there's nothing wrong with having a function as an argument. It just shouldn't be the argument to the unlines function. Okay? So if we leave out the brackets, unlines will try and grab this first argument, and that won't work. So we have to group everything together with brackets in order to prevent unlines from doing that. But there is another way. The reason why we need brackets in there is partly to do with the fact that the operator that's invisible there, the function application operator, associates in a certain way and has a certain precedence. But there's another version of the function application operator. It does exactly the same job, but it has a very low precedence. And that operator is written as $. It's a function application operator, just the same as the regular function application operator, which we can't write down because there's no symbol for it. It takes a function, an argument, and applies the function to the argument to get a result. Okay? So instead of writing brackets around this whole thing, what you can do is use the low precedence function application. This says apply this function to this argument. But because this operator has a low precedence, it has a lower precedence than the invisible operator that sits here in between take 3, rather 3 and take, and the operator that's between 3 and the lines function. Okay? So sometimes this is very convenient. We don't have to write as many brackets all the time by using this $. Now you can, if you want to think of it in very simple terms, just think of the $, as like putting brackets around the rest of the line, okay, roughly speaking. And that's not really what it's doing, but it works roughly like that, okay? So that can be a very useful thing to reduce the number of brackets that you put everywhere. But it's no big deal otherwise. It's just function application, okay? Any questions? So you may see this in typical Haskell code. You may see it also from time to time in the Learn Your Haskell book. We could have also used it here if we wanted to. And it would do the same job. Okay. So this is a right associative operator rather than a left associative one. So what this means is put brackets here and put brackets inside here. Questions? No. All right, cool. Let me take another example, first using zip and then introducing a higher order function that is mentioned in the part B of the lab, zipWith. So let's suppose I want to take a text, a piece of text broken into lines with a new line character, and add a number at the beginning of each line of the text. Okay? So it's going to be a function that takes a string and gives me back a string. But for every line in the string, I'm going to put a number starting at 1 and so on, so that they become numbered lines. Okay? So I'm not going to add I'm not going to uncomment the type here because I'm going to change the type as I go along. That'll be the type I end up with. Okay. So I'm going to number lines for some string will be defined to be, well, the first thing I'm going to have to do is break the string into its lines, just like I did with the other example. And once I've done that, what am I going to do? Well, I'm going to use the zip function. For every line of the string, I'm going to zip a number together with that line. So I'm going to use zip, and I'm going to use zip with the list starting from 1 and going on forever, and the lines. So this is not the right type yet, but this is sort of part of the function. So if I number the lines of the song 2, then I get a list of pairs where the number from the first list is zipped together with the line from the second list. Okay? So now what I want to do is I want to take each of those pairs and I want to turn it into a single line. Okay? So I'm going to build a function for that that's going to take one of these guys and convert it into a single line of text with a number, with some spaces, and then the words. Okay? So I'm going to call that, shall I call it make line, maybe? I don't know. So make line will take a pair of things. Well, okay, let's not do it as a pair. Let's do this as a list comprehension. I'm going to use the make line function together with the number and the line that I get by taking numbers and lines from the zipped list. Okay, so I'm using a list comprehension here. For every number and line pair that I get by building this thing here, I'm going to make a line out of that number and pair. So how do I do that? If I have a number and a line, what do? Well, I need to take the number and turn it into a string representation of that number. How do I do that? Function that turns a number into a string. The show function, thank you. So I show the number, that gives me a string, and I'm going to join that onto a little bit of space. Should we use a tab character? Maybe, that's \t, followed by the line. Okay, so the make line function. So let me just test that out. Scope not in line, so it's num followed by line. Let's try that again. Okay, so let's number the lines from the song. Okay, that's looking all right. And what do I need to do with the result of this whole thing? I want to use unlines to join them all together. Let me just break that over two. Let me just break that over 2 lines there. Okay, so let's have it. Okay, that doesn't look very nice. Let me just put str. I want to display it. What do I want to display? I want to display the number of lines of song 2. You see I'm using my dollar there to avoid having to write brackets. And there I get my numbered lines output, just as I wanted. Now, what was the point of the example? Well, it wasn't just so I could use dollar, but I wanted to point out that this idea of zipping 2 lists together and then using the pieces of the zip lists, applying them to a function to build a new list, is a very common pattern. The thing that changes between different ways you might want to use it is the function. So this actually corresponds to a function called zipWith. I'll call it zipWith prime just so I can define it. It takes a function, it takes 2 lists, and basically performs this computation on it. We could write it as f of E1, E2, where E1, comma, E2 are the elements of the result of zipping L1 together with L2. So that could be a possible definition of zipWith. The definition is not the important thing. The important thing is that the zipWith function exists. So if we were to use this zipWith function instead of doing it this way, what would I do? I would do zipWith. I'm going to zip two lists together using the makeLine function. MakeLine function. And the two lists I'm going to zip together are 1 dot dot and the lines of S. And just check that it does the same job as it did before. Yes, indeed it does. So any questions? Okay, so zipWith is a higher order function which takes a function and two arguments, both of them lists. It zips them together, but not by pairing the results, but by applying a function to them. Okay? All right. Any other questions? All right, well, I'll leave the higher order functions here, and I'm going to switch to another topic.